Hi, my name is Zhang from Huazhong University of Science and Technology in China. This work is cooperated with UC Riverside and Cornell University, main advised by Professor Zhang and Heng. In this presentation, I will introduce Closkye, which aims at protecting sensitive code and data in inter-SGX against the controlled channel attacks. First, what's the inter-SGX? Inter-SGX is a set of instructions that allows developers to create isolated memory regions, called enclaves, to protect users' sensitive information. All the code and data in enclave is unable to be directly accessed by any program outside the enclave itself, including a higher privilege system. When an interruption or an exception arrives during the processing in an enclave, an AEX happens. The processor first saves the enclave's context and then transfers the execution to the OS handler. After the handler returns, the processor restores the enclave's context and resumes the execution where it stopped. So we say, handling an AEX is time-consuming. However, such channel attacks are outside the threat model of its design. By analyzing the memory access pattern of an enclave, many researchers have successfully inferred sensitive information from it. Most such channels can be summarized into three categories, including page table, branch prediction, and cache latency. We studied the existing such channel attacks on SGX and have got two observations. The first one is, in almost all of the such channel attacks, attackers have a similar assumption in which the memory layout of the target program is known, so that by observing the memory addresses, they can know which functions are called or which branches are chosen. The second observation is that almost the previously introduced attacks rely on the page fault subchannel to complete or optimize themselves, because monitoring the execution of the entire program is very time-consuming and unrealistic. So, almost all of the attacks only launch fine-grained attacks after leverage the page fault subchannel to pinpoint functions of their interest. The current defenses can be summarized into two categories. The work in the first category uses the transaction memory to prohibit the generating of AE access. The work in the second category aims at obfuscating the execution of the program, so that they're able to confuse the attackers which part of the program is being accessed. However, existing defenses suffer from three limitations. The first, incomplete protection against even coarse-grained subchannel attacks. Second, incomplete protection of both code and data. Third, high performance overhead. So our goal is to provide an efficient, obfuscated execution against the controlled channel attacks with a tunable trade-off between security guarantees and performance overhead. In this work, we achieve this goal by providing a sub-page level runtime randomization scheme for both code and data. We think this scheme has at least two advantages. First, it can break the fixed relationship of programs' addresses and contents. Second, it stops attacks using the page fault subchannels to locate their interesting functions, so they're forced to monitor all the accesses of code and data at all times, which would make their attacks extremely slow and impractical. We propose the Closkye. At a high level, it acts as a memory subsystem. It consists of two software caches, one execution vcache and one data vcache. A software memory management unit called SMMU, and a virtual main memory. Similar to a physical CPU, all executed instructions are fetched from the execution vcache, and all data is read from and write to the data vcache. Here is an example. we will explain our design with it. In this example, functions for called function bar. The function bar stores constant 1 to a global value ga, then returns to the function for. Every program's code and data is assigned with a logic address at the compiler time. To call bar, the CPU transfers the logic address of the function bar to the SMMU. Next, the SMMU looks up the S-page table and finds the corresponding entry is valid. That means a cache hit, so the SMMU directly translates the bar's logic address to the virtual address in the vcache, and returns the address to the CPU for fetching. Then, the control flow jumps to the bar. The program starts to access GA. Similarly, the CPU transfers the logic address of GA to the SMMU. The SMMU looks up the S-page table but finds the corresponding entry is invalid. That means the vcache missing. The global value does not exist in the data vcache. Then, the SMMU checks the current state of the data vcache but finds all the slots are occupied. So, it randomly selects a minimal page in the data vcache and evicts it to the virtual main memory. Next, it loads the GA's corresponding minimal page to the slot and updates the corresponding SPDE entry. After that, the SMMU translates the GA's logic address to the virtual address in the vcache and returns the address to the CPU for writing. We can see the code and data in the vcache are randomized via frequent replacement at the runtime. The evicting and loading operations between the vcaches and the virtual main memory are vulnerable. Attacks can recover some sensitive information by observing the replacement patterns. To obfuscate the accessing during the execution, SMMU uses the ring ORM protocol to access the virtual main memory. Moreover, because client-side ORM operations including access to the metadata, for example, the stash and the position map are also vulnerable to side-channel attacks. Closkye uses additional protection to make sure all such operations are oblivious under our threat model. We won't introduce too many details about the ring ORM here, but if you are interested in it, please check our paper or the ring ORM paper. After writing the GA, the program returns to the for and continues to run. That's the whole idea of Closkye. The vcache is implicitly re-randomized through frequent replacement, and the ring ORM protocol obscures the replacement. This is the workflow of Closkye. It includes 3 main phases. At the processing phase, a modified compiler extension performs server transformations to build a target program's source code into Closkye's enhanced version. Then, our ORM tree is initialized. All chunks of code and data are moved to the ORM tree. Finally, the enclave starts to run. The runtime acts as a memory subsystem, which obfuscates memory accessing using an enhanced ring ORM protocol. The baseline design of Closkye incurs a high runtime overhead. We think that it mainly comes from 2 aspects. The first one is the software address translation logics, because the baseline version of Closkye incurs list logics before every memory access, which is unnecessary. We think there are a lot of redundant translations that can be eliminated. The second aspect is the vcache missing. However, we cannot prohibit the missing since our vcache replacement algorithms. What we can do is to avoid attrition. Next, from these 2 aspects, I will introduce server technologies about how we optimize Closkye with a few examples. This example shows 2 jumpers. The first jumper transfer to a base block existed in the same minimal page. Because Closkye shuffles both code and data at the granularity of a minimum page. So, the relative distance of the code in the same minimum page are fixed. There is no need to do such translations. We can use relative jumps instead. For each control transfer, Closkye checks if its target address is inside the same minimum page. If so, it eliminates the address translation. In the second example, the for function accesses the global value called GV in a loop. In this situation, there is no need to translate GV's address in every iteration. We can reuse already translated address as long as the corresponding minimum page has not been evicted from the vcache. Closkye moves the translation of GV's address out of the loop's body, so it only needs to translate the address for once. We also call it as the software while TLB. A common compiler optimization is to merge and move constant values to the program's data section. Thereafter, load these constants from the memory into registers during the runtime. However, this causes troubles for Closkye enhanced programs. First, it causes an additional address translation, which is expensive. Second, an access to a constant value in the data section would require loading its corresponding minimum page into the data vcache. Due to the limited size of data vcache, it may finally result in vcache trashing. Closkye embeds constants that ought to be accessed by a basic block into a spare space of the corresponding minimum page. This optimization allows a basic block to use PC relative addressing to access constants without translating a logic address and affecting the data vcache. Since instructions inside loops are repeatedly executed, they account for large portions of a program's execution time. Closkye tries to align loops such that the body of most loops will not cross a minimum page boundary. Our design of Closkye is generic, so the size of the vcache are configurable. Under our thread model, from the security perspective, the ideal size of the vcache is one physical page. However, it's well known that when the vcache size is smaller than the working set of the program, it would end up with trashing. The system will spend most of the time copying data to or from the ORAN-based virtual main memory. Because trashing cannot be avoided through vcache replacement algorithm, from the performance perspective, a large vcache size is preferred. While smaller vcache is implicitly re-randomized via frequent replacement, large vcache requires explicit re-randomized by force flushing. To test the security of Closkye, we replay the JPEG attack, the same to the controlled channel attacks, with different vcache sizes. We can say when the vcache is set to 32 milli pages, even with a low flushing frequency, once after every 1218 address translations, most details become unrecognizable and its pixel distribution is relatively smoother than the one without flushing. We should emphasize that, in this attack, we have given the attack an advantage to precisely distinguish the boundaries of the target functions. But in practice, because the implicit replacement and explicit false flushing in Vcache, it's not easy to distinguish which minimal pages are in the Vcache. The figure shows the additional performance overhead of running DJPEG. The results are around 1 to 3 times. According to our experiments on replaying attacks, we suggest a missing rate at 2.5% can achieve a good balance between the security and performance. In this DJPEG example, it brings about an additional 1.3 times performance overhead. We also have tested all the benchmarks used in the Obfuscated, since the benchmarks program are very simple. We used 4K Vcache sizes. The geometric average slowdown of Closkye is 80%, which is much better than theirs, 51 times overhead, and more evaluations could be found in our paper. In this presentation, we have introduced the several points. Existing defenses either provide an incomplete protection or impose too much performance overhead. Page force side-channel plays an important role in current SGX side-channel attacks. We proposed the Closkye, an efficient obfuscated execution technology, to defend the control channel attacks with a tunable trade-off between security and performance. I'm Pan Zhang. The project will be available soon. Thanks for watching.